Today, I want to talk about operations. Whenever operations is mentioned, one thinks about addition, which is here, subtraction, multiplication, which is here, and division. While those ones are the basic operations, they are not the most basic or the only ones. The most basic one we have is this one, and that is counting. And of course, everybody knows how to count. Counting is normally when you have a 1 and you continue adding 1 each time. So 1, 2. Natural numbers is what we use to count, and that's what we are familiar with. But counting can start from anywhere. So we start 1, 2, 3, 4, 5, and so on and so forth. So that's how we count. So simple. And the operation of counting is the simplest in the list of operations. So that is all about counting. But then let's talk about addition. Okay, this is the next one. Now, addition is simply putting two things together. So when you have two quantities or numbers, you put them together. So let's say you have a quantity A and you want to put it together with B. This is the symbol you use, addition. So addition simply means put together. Okay, so aside from saying put together, how can we represent addition again? In other ways, we can represent addition on the number line as follows. Let's say we have a number line like this, and the 0 is here, and we have 1, we have 2, we have 3, we have 4, and we have 5. Now, if you have, for example, 2 plus 3, this means that you have 2 and you are going to move to the right 3 times, 3 units to the right. Okay, that is addition. But now notice something. Addition is repeated counting. Addition is repeated counting. Addition is repeated counting. Okay, repeated counting. Counting. In the sense that when I started from the 2, I was counting 1 to get 3, 1 to get 4, 1 to now get to the 5. So addition simplifies the process of going unit by unit. Addition simply tells us that move, skip to the next. Don't move unit by unit. And that's what addition does for us. Let's assume you have a number like 7 and they say move to the right by 60. Okay, let's assume for a while you are going to 60 plus 7 and get 67. Okay, let's assume you don't know this, and then you want to do, okay, 8, 9, 10, 11, 12, and so on and so forth. That would waste your time, because by the time you exhaust this 60, you would have been tired. I mean, this 60 may be a number as big as it can be, so you can't do the counting. So that is why you need to use the technique of addition, which simplifies a repeated counting by going straight from here, adding to this place, and you get adding to the 60 to get 67. Simple. So the main idea is that there is a progression from counting to addition. Addition is repeated counting. Since we know addition is repeated counting, we would move to the next operation. The next operation is multiplication. Good. Multiplication is also repeated addition. Okay, multiplication is repeated addition, and let me show you how that works. Let's say that you want to add a number, not to a different number, but to itself, and to itself, and to itself, and to itself, until you get a lot of them. Okay, but you counted each one of them and you found out that there were b of them. Okay, so multiplication simplifies the process for us by saying that simply count how many of the a's are there and say a cross b, where this operation is actually multiplication. And multiplication tells us that there are b of the a's in this operation. You don't need to say a plus a plus a plus a. It has, let me assume 69 plus 69 plus 69 and on and on and on. And let's say there are many of them. If you are going to add and add and add, it will be difficult. So you simply simplify the process and take one of the 69, multiply by the number of them that are there. Let's say n represents how many of them are there. Okay, so n. So that's how what multiplication is. Okay, another way to think about multiplication, I will not represent it on the number line, but multiplication can also be represented on the number line. Okay, but another way to think about multiplication is to think about it as an operation that helps you to count the total number of entities given equal groups of the entities. This is what I mean. Let's say you have a bucket and another bucket and another bucket, and these buckets contain 3 balls each. 3 balls each, okay? 3 balls each. And now you want to know how many balls are in total are there. What you need to do is to use the operation multiplication. That operation will simply help us to know that take the number of balls that is in one of the buckets and multiply by the number of buckets that are there. The number of buckets that are there is 1, 2, 3. So there are 3 baskets of 3 balls, which is 9, and that gives us 1, 2, 3, 4, 5, 6, 7, 8, 9. You don't need to go ahead and add 1, 2, 3 to this. You don't need to count. If you even go by 1, 2, 3, that's counting. If you go by 3, 6, 9, that's addition. Okay, so addition is repeated counting. Remember that. So now multiplication simplifies the process by simply taking a repeated addition and simplifying it to just a number times the number of times the operation has been repeated. Okay, so the number of times we are adding is captured as b. The number of times we are adding is captured as b. Good. Keep that notion and let's move to the next operation that simplifies for us multiplication. Okay, good. Exponentiation simplifies multiplication for us. Not all multiplications, but repeated multiplication. Okay, repeated multiplication. This is what I mean. Let's say you have a times a times a. In the case of the addition, we had a times a, so it's just the same, but here the operation has changed to times. Okay, so we have a lot of a's multiplying by each other. Okay, so the a is multiplying itself many times, but that many times, let's assume we counted the a's and they were b, like there were b of the a's. What exponentiation does is that exponentiation simply says that, okay, the number of times it is the unit is operated with itself, like I mean the one entity is operated with itself, is this. So you take the entity and put the number of times it appears on top here like this, a right superscript. Okay, this tells us simply that a is being multiplied by itself b times. So exponentiation is repeated multiplication. A times a times a times a times a. That's exponentiation. Now, once you understand that, I do not need to go further about what exponentiation is. But imagine for a while you are also thinking about repeated exponentiation. And if you also thought that, okay, if I do this and I want to also simplify it, can I simplify it? Yes, you are right. You can simplify it. There is a way you can also simplify it if you have b of the a's in this tower. The tower, the b counts all the elements in the tower, including the base. So b, a raised to the power a raised to the power a raised to the power a. It includes the base. But that operation is also called tertiation. Okay, tertiation is repeated exponentiation. So I believe you are seeing how the operations build on each other. We started from the basic one, moved to the second basic, third basic, and we are moving to this. And so the most basic one is counting. That's how interconnected they are. Okay, all other operations you have known as basic operations in mathematics will all depend on these ones. Okay, the inverse of counting, I don't think there is a term for that, but the inverse of counting will be uncounting. Let's say you are counting 1 2 3, then you can start from 3 to 1 by removing 1 1 1. So the inverse of counting is uncounting. The inverse of addition is subtraction, the inverse of multiplication is division, the inverse of exponentiation is the logarithm, and the inverse of tertiation is the super root. Okay, but let's now talk about tertiation. Tertiation now tells us that if you have a power tower like this, what you need to do is write the base and write the b as a left superscript. So tertiation simply allows you to simplify a power tower into this format. Okay, you write the base and write the number of times the operation is done, or the number of times the base is repeated in the power tower as a left superscript. But if you're also wondering whether there is something like a repeated tertiation, where you have a special operation also representing repeated tertiation, you are not wrong. There is, and that is called pentation. Okay, so now you know the basic operations, and then you have an idea that the operations keep on moving forward until you have a lot of hyper operations, like you just have a lot of them. But the basic idea is from counting you go to addition, and from there you go to multiplication, exponentiation, tertiation, pentation, heptation. They keep on moving. Okay, and sorry, the higher you go, the crazier it becomes, because even, let's see, counting, there is no growth like that. Addition, you add two numbers, there is no big growth. Let's say you add let's say you have a number like 2 plus 3, no big growth, the answer is 5. And you have a number like 2 times 3, 6. Okay, 2 raised to the power 3, that is 8. And you have 2 tertiated 3 times, that is 16. The growth is quite slow because the number is 2. But if we use 3, or we use large numbers like 4, even by the time we reach tertiation, we can't have space for it to be tertiated. Okay, so there is a rapid growth as you go from the most basic operation to the high operations. So counting doesn't actually have a notation. We know how to count, so that one doesn't have a notation. But addition, we all know it's a plus b. But another way to write it in the order of the operations is counting. We always write it with a notation like this. We have the first number and the operation order, the order of the operation, times b. We put braces like this, we put brackets like this, and we put the number it represents there. So counting has a 0, addition has 1, addition is the 1 is the first, counting is 0, and multiplication is second, so 2, exponentiation is third, so it takes a 3. We have tertiation being the fourth, so it takes a 4. These notations are quite easier to write because they give you the luxury to put any n. So A5 for pentation, A6 for hexation. So this particular notation is called the square bracket notation. Okay, but there are other notations as well. I think I need to change the paper and show you, but I'll make another video to focus on the notations. Okay, so the other notations, we have another notation we call the general notation, and that notation is like this. So where the first A and B occupy, like, they are the arguments of this particular operation, but then n is the level. So n is the 0, 1, 2, and so on and so forth, where 0 represents the counting. So this is the general notation. The square bracket notation is the A square bracket n B. Okay, this is the square bracket notation. N still represents the level of the operation, while A and B represents the base and then the number of operations that are taking place respectively. Now there is another notation called the Knuth's notation, or Knuth's up arrow notation. Knuth's up arrow notation. So the Knuth's up arrow notation, unfortunately, counting doesn't have a notation like that. The Knuth's up arrow notation starts with the multiplication. So multiplication, if you are multiplying, it's also the same as when you say A up arrow B. If you are raising A to the power, multiplication doesn't have an up arrow notation. The up arrow notation starts from exponentiation, where you have A up arrow B, meaning exponentiation. And for tetrahedration, you have A up arrow B, meaning A tetrahedred B times. And for pentation doesn't actually have the superscript subscript notation, but pentation has the Knuth's arrow notation as A up arrow B, 3 up arrows, and that is how it goes for the rest of the hyperoperations. But generally, this one is used. I do like these two, but the Knuth's up arrow notation is also used in a lot of mathematical papers.